So let's recap Cartesian geometry, our coordinate geometry, and some of the formulas. Distance formula, of course, the square root of x2 minus x1 squared plus y2 minus y1 squared. Some people get hung up about the x2 and the x1 and which is which, and it doesn't really matter at the end of the day because you're going to be squaring it, so you can't get it in the wrong order. Simple little question there. Find the distance between the two. So really you're just saying difference in the x values squared, difference in the y values squared, and we come up with 2 root 5. Essentially it's Pythagoras' theorem, because that's what you're doing on the number plane. The line's at an angle and you're just saying, well, what's the length of the hypotenuse? I know the distance between the x values, I know the distance between the y values, so I can work out the length of the hypotenuse. That's the distance formula. The other one that we see a lot, of course, is the midpoint formula. And a midpoint is exactly what the name suggests. It's the point that's in the middle of another 2 points. The average, if you like. So that's what we do here. We average the x values, we average the y values. If I find the midpoint, average the x values, average the y values, we get the midpoint. Euclidean geometry, Cartesian geometry, it's all geometry. And so sometimes we use Euclidean geometry to solve Cartesian geometry problems. So a knowledge of Euclidean geometry can be useful. Quadrilaterals then. So how do we classify our quadrilaterals? Well, we classify them depending on the features that the characteristics of the quadrilateral, if you like. So there's the quadrilateral family, a lovely little flow chart. As you go down, they get more specialised. So the example I put there was the rhombus. The rhombus would have all the features of a kite, a parallelogram, a trapezium, a quadrilateral. So we start off with the quadrilateral. What do we know about it? Well, pretty boring. It's got 4 sides. Not that useful. It's got 4 angles. That's pretty much it. It's just a 4-sided shape. But we get more specialised. I can branch off to the kite. The kite is the one where we have adjacent sides equal. So a pair of adjacent sides equal. The diagonals in a kite we know are perpendicular to each other. And we have a formula for the area of a kite. Now, people often mistake this for the formula for an area of a rhombus. It's not the formula for the area of a rhombus, it's the formula for the area of a kite. So half the product of the diagonals. I could branch out to the trapezium. The trapezium has 1 pair of parallel sides. And its formula for area, half the height, which is the distance between the parallel sides, the perpendicular height, times the sum of those parallel sides. Branches down to the parallelogram, where we now have 2 pairs of parallel sides. But you could use the formula for the area of a trapezium to find the area of a parallelogram if you wanted to. It would work. But we have additional information. We now know that the opposite sides in the parallelogram are the same length. So that might be a fact we could use. Opposite angles in a parallelogram are always equal. Notice my abbreviations here too, by the way. When we are writing regions, it's okay to use acceptable geometric abbreviations. So you'll notice instead of writing the word parallel on parallelogram, I just put 2 parallel lines. So parallelogram. Perfectly acceptable. The angle symbol for an angle. But I don't just make things up. I don't write quad for quadrilateral. I mean, that's not a known abbreviation. We only use known abbreviations. Diagonals in a parallelogram bisect each other. And the formula we use is base times height. Again, the height is the perpendicular height between the 2 sides. Another way of proving a shape is a parallelogram. I mean, we could use any one of these features, but this one's interesting. If you've just got 1 pair of sides and you know they're both equal and parallel, then it's got to be a parallelogram. So you don't have to do it for all the sides. You can just get 1 pair of sides there. Okay. The parallelogram branches off to the rectangle, where we know, oh, now the actual angle is 90 degrees. So it gets a little bit more specialised. The diagonals now become equal. And length times breadth, of course, the area formula. So now the rhombus, which is both a kite and a parallelogram. And that's why we often say the area of a rhombus is half the product of the diagonals, because the rhombus is a kite. And so we can use the formula for a kite. What else do we know about a rhombus? Well, we now know the diagonals in a rhombus bisect the vertex. So that's how it becomes more specialised. That all branches down to the perfect quadrilateral, the square. It possesses every feature of every quadrilateral. If we really wanted to, we could write a formula for it. It's the side length squared. Hence the name of the shape, square, I guess. Okay, so we get a problem like this then. The points A, B, C and D form this quadrilateral. We want to show that this shape is a rhombus. Now, there's lots of ways we could do it. We could say, well, the opposite sides are equal and parallel, but that would make it a parallelogram. How do I make it a rhombus? Oh, now if I got adjacent sides are equal, that would make it a kite. Oh, well, it's a kite and a parallelogram. Must be a rhombus. How did I do it? Let's have a look. I found the midpoint of AC, and it's 5 on 2 minus a half. Then I went and found the midpoint of BD. It's the same point. Well, that tells me it's a parallelogram. Right? The diagonals bisect each other. That was a feature of the parallelogram. So all I had to do was find the midpoint. I know it's a parallelogram. I found the length of CD, then I found the length of AD. Hang on, I now have a pair of adjacent sides that are equal. So I've got a parallelogram where adjacent sides are equal, got to be a rhombus. Alright, so 7A, start off the term with that. Just some coordinate geometry problems.